Today we will bring you a new paper, Individual Mobility Prediction Review, Data, Problem, Method and Application. This article was written Zhenliang Ma. Next, I will introduce the abstract. The sharing, business models and on-demand services have been altering city dwellers' travel habits from buying the means of transport to buying mobility services based on needs. The capability to proactively provide personalized services is the future of smart multim, in which the individual mobility prediction technique is a key enabler to achieve that. With the advancement of data collection and computing techniques, the individual mobility prediction problem has been gaining increasing interest, but yet receives little attention in applications and differs in problem definitions and methodologies developed given varied data sources and application contexts. In addition, there are many review studies on collective mobility predictions, but no review study on the individual mobility prediction. To address these issues and fill the gap, the review synthesizes existing studies on individual mobility prediction in transport, identifies remaining research needs, as well as discusses methodological considerations and potential future transport applications. The review highlights the value of individual mobility prediction in driving proactive service provisions and mobility management in multimodal mobility systems. Methodologically, it is critical to pay more attention to data validation, data specification, and model interpretability in developing learning-based prediction models. Practically, it is of high value to study the individual mobility prediction with arbitrary prediction times and prediction horizons. The methodology adopted involves the following steps: statistical model, deep learning-based model and performance metrics. Statistical models have been widely used in individual mobility prediction. They model the mobility sequence dependencies using probabilistic models, such as the Markov chain and its decision trees, and natural language models. Deep learning-based individual mobility prediction methods have been emerging in recent years. They are capable of capturing both higher-order spatial temporal dependencies and longitudinal and periodic features, thus achieving superior performance than statistical models. Generally, the response variables of the individual mobility prediction are discrete or categorical, for example, origin, destination station, grid number, time periods, etc. Thus, the individual mobility prediction belongs to a multi-class classification problem. The classification metrics are used in validating the model performance, accuracy. The individual mobility prediction accuracy is the fraction of correctly predicted samples. Top K accuracy. The top K accuracy extends action by defining right as the number of sample instances, correctly predicted by the top K candidates ordered by probabilities. Root mean square error, RMSE. RMSE is the standard deviation of prediction residuals. Individuals and infrastructures are increasingly interconnected, allowing effective communication. The introduction of the mobile internet and the apps ecosystem has changed the way transport systems communicate with their customers. These technological advances conveniently link passengers and SV, such as personalized travel recommendations, pricing, and incentives. Personalized service recommendation is important in terms of both location, point route recommendations. The mobility service recommendation systems highly depend on the precise individual mobility prediction. For example, in POI recommendations, traditional matrix factorization-based algorithms cannot utilize the sequential dependencies of individuals' mobility records, thus can only provide general recommendations based on comprehensive mobility patterns. Ignoring the individual trip contexts could lead to biased predictions. For example, a commuter regularly travels between home and office, but he may also have some infrequent travel patterns, such as visiting places for entertainment on Friday evenings. The traditional recommendation models may only predict the regular travel places without incorporating the individual's trip contexts as the individual mobility prediction model does. The same conclusions on the value of penalization are, but lack attention on drivers' personalized preferences. New technologies have been transforming the mobility management paradigm from generic and static to a personalized and dynamic manner, in which the mobility management schemes are customized to individuals and their trips. For example, the San Francisco Bay Area Rapid Transit piloted the BART Perks Phase 2 incentive program in 2019. Personalized incentive mobility management strategies were also implemented in car traffic and discussed in the new and future urban mobility area with multimodal operations and connected autonomous vehicles. For example, Los Angeles conducted a 10-week pilot field study in 2013, and 35% of travelers changed their departure times and route choices. New York City introduced the Bike Angels incentive program in 2017 that offers points for city bike riders who improve the availability of bikes and docks for fellow riders. Riders get various rewards with different point levels. Transportation Network Company offers trip discounts to improve shareability opportunities by encouraging sharing, walking, and waiting. Individual mobility prediction drives proactive and personalized service provision and mobility management that are essential for multimodal mobility travels. The advancement of connected technologies and computing techniques enables large-scale individual mobility data collection and prediction. Data validation is critical to ensure mobility data quality, correct and useful for downstream analysis and applications. Most individual mobility prediction problems are defined to predict the next trip location whenever a trip record is collected. Secondly, mathematically, the individual mobility prediction and NLP problems are both sequential modeling problems, thus sharing the same model structure essence. The methods proposed in NLP studies could potentially be adopted for individual mobility prediction. The NLP area advances significantly in recent years in machine translation, named entity recognition. We discuss the potential of these emerging models in enhancing individual mobility prediction performance. Thirdly, it is important to define the interpretability of deep learning-based individual mobility prediction models in the transport domain, and develop the interpretability analysis framework and quantification indicators. Also, future research may explore the higher-level interpretation of the model. Finally, individual mobility prediction is still an emerging area. It is a technique enabler to shift the personalization paradigm from the reactive to the proactive mode in transport. It is envisioned to contribute multimodal transport areas in service provision, operation planning, and mobility management.